Okay, good morning everybody. My name is Mietek Bakowski. I'm a manager of Wide-Bandgap Power Center at RISE and lead organizer of this event. SCAPE workshop with focus on applications has been organized since 2007. At that time, the only application was switch mode power supplies using silicon carbide Schottky diodes. Situation is dramatically different today. As we all know, wide-bandgap technology is about energy efficiency, which means efficient use of electric energy. Adoption of silicon carbide and GaN devices translates in many applications into 50% savings of electric energy, and has a truly revolutionizing effect on energy conversion systems, thanks to dramatically lower conduction losses and also switching losses due to fast switching. It has also wider implications for the technology development, industrial development, and economy. Wide-bandgap technology is not a substitution technology. Simply exchanging silicon devices with silicon carbide or GaN will not do. Full utilization of advantages of this technology requires and stimulates innovations in areas of low inductive packaging and converter designs, packaging materials and passive components. To secure high volume supply of wide-bandgap devices, it places new requirements on manufacturing and testing. In short, the ever-increasing demand for electric energy creates market for attractive, energy-efficient power electronic products, and wide-bandgap technology facilitates realization of such products. We created Wide-Bandgap Power Center 2011 with a mission to promote adoption of silicon carbide devices in applications and to provide a cooperation platform for power electronic industry, academia, and institutes. In the opening presentation today, we will hear from Victor Veliadis, Executive Director and CTO of Power America, organizations sharing the same mission, about their program and achievements. We will also hear from the Director of Advanced Power Electronics Research Center, IST in Japan, about their achievements. We have been impressed over the years by the long-term government-supported development programs in SiC devices in Japan, going on since the middle of 1990s. IST has been at the center of these programs. We will also hear from Power Electronic Conversion Technology Annex, PECTA, within the International Energy Agency, that has the objective to promote wide-bandgap-based power electronics by government approaches and international standardization. We are experiencing, I believe, the third and this time successful wave of interest in silicon carbide. It has been going on for 30 years now. During that time, almost all power device concepts in the book on power electronic devices has been tested and demonstrated by R&D teams in US, Asia, and Europe. Basically, only two unipolar device concepts have made it to commercialization, and those are MOSFET and JFET. It took a long time to develop silicon carbide MOSFET due to the challenges related to the quality of gate of the dielectric and silicon carbide interface, resulting in low channel mobility and reliability issues. We will have an illustration of that tomorrow in a talk by Ivar Shlelis. JFET had a problem of its own, being a basically normally on device, until a solution was adopted, as we will hear from presentation of Anup Bhala from United Silicon Carbide. GaN is developing at a speed that surprises many, considering that devices were to begin at not only normally on, but also lateral, limited in voltage and power density, and built on material with dislocation density orders of magnitude higher than this in silicon carbide. We will have a better picture of commercial GaN and its merits after a keynote talk by Gerald Dubois later today. There is also a long-term work on vertical GaN devices that could open the high voltage, high power density sector for GaN, as we will hear from Herbert Pyrich, coordinator of European Ultimate GaN project. Qualification work on wide-bandgap devices is ongoing in the international community. JEDEC and the ISiCPEAW committees are two examples, and automotive applications set especially demanding requirements. In reliability session, we will hear more from Korean Automotive Technology Institute, KATEC. There are ongoing European efforts by rail companies in Shift to Rail program to develop and innovate rail system in Europe. We will hear two contributions from a related research project, Reset for Rail, on reliability of 3.3 kilovolt silicon carbide traction modules, and on wireless charging for rail. We will hear tomorrow in reliability and medium voltage converters session. During the last decade, we observed trends of vertical integration, meaning creation of in-house supply chain from material to discrete devices and power modules, leading to acquisitions and mergers. As a local example from Kista, Stockholm, the two spin-off companies, Transig from KTH and Ascatron from our institute, have been acquired by bigger players during the last 10 years. Tomorrow, we will have a market overview by Claire Truadec from Yole Development, and panel discussion with invited participants representing both device manufacturers and users. And learn much more. Do not miss that. Also tomorrow, we will be able to peek inside the packages of silicon carbide and GaN devices for tear down and cost analysis by System Plus Consulting. I hope we all have a rewarding workshop. So now I would like to invite Victor Veliadis from Power America to open for the opening presentation.
So thank you so much, Mitek. First of all, I would like to say that it's good to be in one place with everybody physically. I missed that interaction. And before I proceed, I'd like to thank the organizing committee. I've organized events, and I know there's a lot of work that goes into that. So Mitek and team, thank you so much for putting this together for us. So what I will talk about is accelerating commercialization of wide-bandgap power electronics in the United States, and emphasize a little more silicon carbide. So the first thing that I wanted you to notice is that silicon carbide and GaN field than that of silicon. So that's number one. And secondly, the band gap, it's about 3 times larger. So those are compelling properties that have led to a lot of investment in silicon carbide and GaN over the years. So with respect to a device, if you look at this thick layer that holds the high voltage, the thickness of that layer is inversely proportional to the critical electric field. So if your critical electric field is 10 times higher, your device will be 10 times thinner for the exact same breakdown voltage capability. And if you look at the device resistance of this thick layer that holds the high voltage, it's inversely proportional to the third power of the critical electric field. So if your critical electric field is 10 times higher, then the resistance in principle can be 1,000 times less. So what does that mean? The fact that we have a large band gap and a very high critical electric field, it means we can make silicon carbide, GaN, we can make devices with thinner layers. So thinner layers means low resistance, lower conduction losses. And of course, the fact that you have a wide band gap means that your leakage is lower because thermally excited carriers now have a bigger band gap to go through. And you can see that from this equation here, which is the, the room temperature. And of course, thinner layers and lower specific on resistance means that the device will be smaller, capacitance will be smaller, you can operate at higher frequency. And operating at higher frequencies is the key selling point for silicon carbide and GaN, because it allows you to simplify a lot of the system components. And of course, if you look at silicon carbide in particular, the thermal conductivity is higher, so therefore you can basically have simplified thermal management. So today, and this is a graph by Infineon, we have silicon carbide, and GaN. They're all available. They're commercial off-the-shelf solutions from many vendors. So the question is, what is the best technology? What do we use? And there's no single answer. You use the best technology given your specific application, and that's key. There are certain applications, for example, you have high voltage, you might have very high current requirements. In certain applications, you might have very high density requirements, efficiency, temperature, and of course the cost consideration. So it's kind of a complex decision, but all three technologies are available. And just very roughly speaking, silicon, it's king, 15 to 650 volts. GaN from 100 to 900 volts does very well, the lateral version. And of course, silicon carbide started at 1.2 kV and goes all the way out to these very high voltages and does extremely well. And really, the battleground today is at 650 volts, where silicon IGBTs are very, very competitive. You have a lot of lateral GaN solutions at that 650 volt level. And of course, silicon carbide started at 1200 volts because it was sufficiently removed from where silicon is very competitive. And because of that market at 650, it worked its way down. There isn't 650 apart from the power supplies. Today's electric vehicle, the majority of them have a 600 volt battery for a 400 volt bus. So these are the right type of devices. So if you look at silicon, of course, it's very reliable, rugged, it's very cheap. You can do very high currents. And very important, there's the device and circuit design legacy. People know how to design with silicon, okay? And that's what I think Metek also mentioned, that you cannot just take a silicon device and insert silicon carbide and GaN and expect to see improvement. For GaN, it's very efficient, high frequency operation at reasonable cost. The lateral GaN devices are Cmos compatible. They're made in large volume fabs, which brings the cost down. And of course, silicon carbide is efficient. You can operate at high temperature and high frequency, and there are certain non-CMOS processes that you need to be aware of if you're going to fabricate silicon carbide. Okay, so with respect to device frequency, as you go higher in frequencies, the silicon solutions become less and less attractive, and really the silicon carbide and GaN system opportunity space is here. You know, you want to have the high powers and high frequencies. And this space here basically translates to a lot of applications. At the very high voltages, you have the DC transmission. You also have the AC transmission, motor drives, power supplies, automotive, etc. So the biggest application for every new technology to really catch on, you need to get to large volumes so you can take advantage of economies of scale. Okay? For the longest time, if you were to go back in 2012, out to 2016, 2017, photovoltaic was the big application for silicon carbide in particular, and then electric vehicles came along, which is a mass application where silicon carbide and GaN, for that matter, bring a lot of advantages. So this is like the big application that leads to high volumes, to economies of scale, and it's multiple parts. Apart from the traction inverter, you have the onboard charger, very big application there, and the DC-DC converter. And of course, Tesla, as we know, with ST Microelectronics MOSFETs back in 2018, opened up the road, and then everybody's kind of rushing to take advantage of the silicon carbide benefits. Now, one key item that's happening in electric vehicles is we're moving from the 400 volt bus to the 800 volt bus. And why are we doing that? It's higher efficiency, so you get longer range. You can do faster charging and cost reduction. There's this graph from Yol, and we'll hear from them tomorrow in detail. But you can see that the power market is starting to become, you know, silicon carbide and GaN are about 15% or even more. And that's a really, really big application, because as you move higher in voltage, that's where silicon carbide and GaN become more competitive compared to silicon. Now, with GaN, it's at 650 volts. It's a lateral device. Increasing it to 1200 volts, because this is what you need for 800 volts, is not trivial. You want to develop vertical GaN, or maybe you want to do a 3-level with GaN device, which will mean more devices versus a 2-level with silicon carbide. So that's yet to be determined. And part of what we do at Power America, where we run projects, we're going to be running a projects where we're going to be comparing an inverter with 1200-volt MOSFETs versus an inverter using 3-level 650-volt GaN devices, commercially available devices. So that's the big application. Okay, and again, one more graph from Yoel. As you can see, the automotive, the EV automotive market is going to be the dominant silicon carbide market for years to come. Okay, so let's look at some of the specifics now for the silicon carbide technology. First of all is the substrate. Any new material, gallium oxide, diamond, aluminum nitride, gallium nitride, you need to have substrates that are cheap and can compete with those of silicon. So cheap and low defects, planar, and so on and so forth. Well, with silicon carbide, there is a problem, right? It's, you need to go at very high temperatures, 2,300 to 2,500, versus 1,500 degrees for silicon. And in silicon, you basically have a melt, and you're pulling the material, and this necking process helps you reduce the number of defects. And that's not the case in silicon carbide, where you need a very good seed layer. So with silicon carbide, the process of making the substrate is more labor intensive. The boule is a lot slower to make. It's a lot smaller in length. Diameter is a problem. You have limited crystal expansion, and because it's a very, very hard material, polishing is a problem. So what does all this come down to? It comes down to the fact that the silicon carbide wafer represents about 50 to 70% of the silicon device cost, depending, of course, on who you ask. And that's a very big amount of money to pay for the substrate itself. And this is really what's driving the vertical integration that we're seeing today. Any company that knows how to make a substrate, because the learning curve is a very, very steep one for the substrate, any company that knows how to make a silicon carbide substrate is pretty much sitting on gold. And some of the examples, if you look at GT Advanced Technologies, right, they were making ovens, they were selling ovens for silicon carbide boules. Well, they realized that selling the oven with a recipe is actually very, very valuable. The recipe itself is very, very valuable. So what they did is then they became a producer of volume, and as expected, onsemi wanted to have an internal supply of silicon carbide to reduce this margin, to drop it maybe from 50 to 70 to around 40, so they were bought. Another example, of course, is Infineon. It acquires Electra. They have a more they have a process of, I guess, slicing the wafer, like cold split, I think they call it, where they can take advantage of less material waste. Another big example is of course, 2.6, right? I was talking to 2.6 15 years ago, and I said, you guys make the substrate, why don't you just put the epi and have, you know, like a bigger solution? And the answer was, we thought about that very carefully. We don't want to compete with our customers. Now, if you have the substrate, you probably, in my mind, have the biggest building block to having a silicon carbide, you know, production, right, where you can make a lot of money. And the vertical integration, 2.6 is basically acquired Ascatron, and you guys here are here from Ascatron, big success. And of course, the GE process to fabricate at a fab at X-Fab. So that's a very good example of vertical integration. And also take into consideration that anytime there is a very difficult way of making anything, there are going to be disruptive technologies. Well, how about if there's a way to get silicon carbide substrates where you don't need to go to 2,500 degrees, where you don't need a nice, large, clean seed, and you can make a wafer at much lower cost. So engineering substrates are a very big business. Soitec has announced some products, and there are other companies out there that are working in that technology. So moving forward, the substrate will remain to be key. All the big players, Infineon, STMicroelectronics, you know, they're moving in the direction of trying to have an internal substrate supply in order to reduce the cost margin. Okay, and of course, one big thing would be to move to 200 millimeters. 200 millimeters in silicon was 1992, right? So we're about 30 years behind with silicon carbide. And one can say, okay, if I go from 150 millimeters to 200, I'll have 40% more devices. That's a 40% reduction of cost. That's not going to be the case, of course, because we all know that whether you process a 150 or 200 millimeter wafer in the fab, the cost of processing is approximately the same, but the cost of material now will be a lot more expensive. When I was talking to Wolfspeed, they told me that releasing 200 millimeters, the goal is to have the same or lower cost per centimeter square compared to 150 millimeter wafers, and of course, same or lower defect density. If you assume that 200 millimeter wafers will be released with same cost per centimeter square because of the higher cost of the wafer, and because you're going to have a 500 micron thick wafer versus 350, so you're going to need a lot more material. I estimate initially about a 20% decrease in cost if you move to 200 millimeter. And there's a number of companies out there that do 200 millimeter work. They want to get into silicon carbide, and I talk to them, they say, well, we don't want to have to retool everything to 150 millimeters, go back, we want to move forward. So there are a lot of companies that are waiting for this to happen, and they're going to jump in and start producing, which of course is a big thing. The more players, the more the cost will go down. Okay, so just to give you some idea, you have this mature CMOS compatible process from silicon, okay? You're not going to reinvent the wheel. You want to take everything you have from silicon and use it, but the specific properties of silicon carbide, the hardness of the material, necessitate some new processes that are not available in silicon. So here's a summary of what those are. You need to etch, right? It's a very hard material, so the resist mask will no longer be good. The selectivity is very bad, so you need a hard mask, and you need to develop that. The second thing is you need to thin the substrate, because at lower voltages, like 1200 volts and below, the substrate itself is the biggest contributor to resistance. Substrate, then it's a channel resistance, and the drift layer that holds the high voltage comes third. So thinning the substrate, you need to find ways to do that. Doping, okay? You need to have heated implantation, and even that's not good enough. Then you need to do an anneal to activate the dopants and recrystallize the wafer. Metallization, you need to have CT matched materials, so things like tungsten, molybdenum, tight tungsten, those are good materials, and you need to know how to put them in your device. Ohmic contact formation, because of the high band gap, if you put metal on silicon carbide, you're going to get a Schottky. So the question is, how do you get a low resistivity ohmic contact in silicon carbide? Another process that needs to be developed. The gate oxides, the silicon carbide oxide interface has a lot of traps, and that can lead to a lot of threshold voltage instability, and we'll hear about that tomorrow from my friend Ivars Lelis. And that's something where a lot of work has gone in, and there's a lot of room for improvement here, a lot of room for improvement. The wafers are transparent, of course, because of the wavelength of silicon carbide. So if you try to use your silicon tools that use optical beams and silicon is opaque, then they're not going to work. Now, in the old days, when I was playing around and doing all these things in 2004 and on, I had to find ways to use the silicon tool to do the metrology. Today, silicon carbide is big enough that companies like KLA and others are making specific tools for the wavelengths that are needed for silicon carbide. The relative lack of flatness, that's a really big one. Silicon is flat. I was seeing a presentation, it was saying that silicon, the flatness of silicon is like a tennis ball. If you take the area of Japan, Korea, and Taiwan, that big area, with silicon carbide, the planarity is not very good, and when you get to that implant, 1600-degree implant activation, you can actually sometimes see a wafer turn into a potato chip, okay? And that's not good, because you will not be able to focus with a stepper. So planar wafers are a very big thing, of course, lowering the defects as well. And of course, the insulation dielectrics, because you cannot get a thick thermal oxide, you have to deposit your oxides, and anytime you deposit, there are going to be contaminants that might interfere with the performance of your device. So do not despair. If you go into a silicon fab, right, that's about 20, 25 years old, fully depreciated, 90 nanometers or even 140 will work for the silicon carbide dimensions. So you can take an old fab, take the silicon tools, and buy some specific tools for silicon carbide. Now, a few years ago, when I was looking into that, when we did it at XFab in Texas, it was about $15 million for the equipment. I know inflation prices have gone up, but maybe a $20 million investment will allow you to take a silicon fab and put the tools for silicon carbide. And that's not a lot of money. It's not the billions that you need in order to do the latest and greatest node. So silicon carbide has the potential to breathe life into all fully depreciated, mature fabs and bring the volume up again to get them to work close to capacity, which is the only way, of course, you're going to be profitable if you're running a fab. Okay, so some of the example of my old work and shortcomings. You can see here I'm trying to do this vertical pillars, 0.7 microns. I put a metal mask because you cannot use resist. The selectivity is bad. Metal mask, as I do the RE chips off, creates this little microtrenching issue, which are called grass. highly undesirable. So what I did next, I'm like, okay, let me heat this up and eat those little silicon carbide pillars away. And it kind of helped, but it also shrinked the size of my pillars, right? That's not a good way to do it. But, you know, you play long enough, right, with the tool and the mask and the, you know, the aluminum chrome aluminum deposition chrome is basically for adhesion. You don't want to put aluminum directly on silicon carbide. And you can see these are nice vertical sidewalls, 0.7 micron, very clean. Another example is with the implantation. This is before implantation, and this is after the 400-degree heated implantation. And you can see that the wafer now becomes opaque. So you just took a nice crystalline wafer and turned it into glass, despite the fact that you do a heat implantation. What do you need to do next? You basically need to take this wafer, drive it to anywhere between 1600 to 1700 degrees, anneal it in order for the crystallinity to come back and the dopants to be activated. Now, you need to put a special coating to do this right. This wafer did not receive a coating. I gave it to my technician. I gave him the recipe for the coating. Instead of putting it on the front of the wafer, he put it on the back. Didn't work that well. But at the same time, some wafers from that same lot got the, you know, the coating where it needed to be. So I was in this situation where I saw this and this result from the same lot, same wafers. So moral of the story is you have to develop these processes. You have to know how to do the coatings. You have to know how to do specific things for silicon carbide. And keep in mind that unlike silicon, where you compete on design, in silicon carbide, people compete on design and on the process steps. People have specific IP in process steps, and they do things in certain ways. And that's why you'll see devices from different manufacturers fail differently, because some of the process steps are different. We haven't reached the level of uniformity now where there's like a, you know, an omni type of process for each one of the silicon carbide processes. Okay, silicide. This is basically putting nickel on source and gate areas. You can see this Swiss cheese structure is the signature of the implantation. So you put the nickel down, you're going to have a Schottky view. Stop there. So you got to do an anneal. Silicon, an RTA silicon tool, 900 degrees for about a minute and a half will give you a very nice silicide. This is a situation before I used this glass, this BPSG, to isolate the source from the gates. And you can see with the silicide, you get these whiskers. So if these whiskers go from gate to source, you got a short. And I saw that, and it got shorted, and I put it in the oven, brought it to high temperature just to kind of melt those connections away, and the device worked. But this is basically going from here with this glass separation. You get a nice silicide, low ohmic contacts, and you put a thick metal, and you're done with that. Okay, so let's look at the manufacturing situation. In the United States, of course, silicon carbide has massive, massive defense applications, from electric vehicles from the Army to electromagnetic gun, to the catapult, to electromagnetic armor, a whole bunch of things. And I was kind of surprised, you know, to see electric vehicles pursued by the Army in the early 2000s. And I'm like, okay, is the United States feeling that, you know, you got to kill in an environmentally responsible way? That was not the case, okay? They bring significant advantages, because when you go in electric mode, you don't produce heat, no heat-seeking missiles. And if you have silicon carbide, because of its ability to withstand higher temperatures, if something hits your cooling system, you might just have enough energy before the electronics melt to get away from the target zone. So the United States basically invested massively at the very beginning in silicon carbide technology. So this is a Yole graph from 2013, and it shows the infrastructure for silicon, right? You got the IDMs that go all the way from manufacturing to marketing, selling products. You have the foundries that do manufacturing for everybody. You have fabless companies that basically go to the foundries, and you have design houses. And that's your silicon world. And let's see what happens at silicon carbide. So in the United States, Wolfspeed, Microspeed, GE, we have IDMs and onsemi that work really, really well. We set up the first foundry in the United States, X-Fab Silicon Foundry, bought the silicon carbide tools, $15 million investment, and they started running silicon carbide, complementing their silicon work with silicon carbide. A number of fabless companies. These were all basically fabless companies. This was United Silicon Carbide. We hear from Anoop tomorrow. It's part of Qorvo now. And all these companies started manufacturing at X-Fab. The model is successful, of course. You have Microchip, that has its own manufacturing, but also goes to X-FAB as well as risk mitigation, or in case there's a high volume and a need. And design houses are just basically some universities that put together a process, and they just sell to get licensing fees. So the silicon infrastructure has been duplicated in silicon carbide very successfully in the United States, and of course you have ST, Infineon, Rome around the world, no shortage of good places. And keep in mind that in the silicon foundry, you got to compete on the process in addition to the design. And of course, the wafer quality and supply is an issue. It's not like silicon where wafers are abundant and cheap. Okay, so some of the barriers to mass wide-bandgap commercialization. Of course, the high device cost, that's the first thing people will tell you. People have concern with defects, reliability, ruggedness. Is it as good as silicon? Do we need to wait? Is the time here yet? And I think Tesla gave a pretty good answer to all that, and everybody's kind of running to catch up. And of course, need for workforce training, right? If people don't understand how to insert silicon carbide and GaN devices, if they don't understand the high frequency aspects, the cooling, all that, then it's not going to move forward. So in the United States, Power America is a consortium of companies. We do silicon carbide, GaN, from fabrication to equipment manufacturers to applications. And we have a number of universities from the United States and labs that work with us, and we solve problems in wide-bandgap technology. So the strategy that I followed is one from bottoms up. I wanted to streamline fabrication, develop the modules, of course, right? Because without a module, a module is, you have the silicon carbide device or GaN device, like the Ferrari engine, and if you put it in a Honda Civic or in a little Fiat, you're not going to get the performance. The Ferrari engine needs the Ferrari car. So you need to have the right module for the high frequency, high temperature, high current, and high voltage isolation. And then I worked on training the workforce, investing in training the workforce and establishing the reliability. Then you get to the point where you put them into the systems. And that's really crucial, because maybe the upper management of the company is not willing to write the check to look into this new technology. But when you come and fund and they see the results and they understand their competitive advantages, then they will follow up with their own money. And this is what you want to do. You want to take the taxpayer money and you want to invest it in a way that will lead to growth. So you put that seed money and multiply the growth. And then with that, you get to large volume manufacturing, which is crucial, which lowers the cost. And then you go to large scale power electronics adoption, the mass commercialization. So I'm proud to say that over the last 6 years, I had $146 million that I invested in 200 projects. You can see the areas from low voltage silicon carbide, modules, GaN applications, silicon carbide applications, and a lot of education projects. So in that process, I trained 410 full-time students. And why is this crucial? Because every one of those students will go out in the industry. And the projects I had were collaborations of industry and university, because you don't want a professor running off to do some hero result. I wanted something that was applicable, that led to manufacturing. So these students now are in industry, multiplying silicon carbide and GaN, or at universities teaching. And again, if somebody is not comfortable, doesn't know enough about silicon carbide and GaN, he's not going to risk his career trying to insert them, and then something happens with reliability, something fails, and then he has to answer to his boss. So the easiest thing to do is do nothing and continue doing the silicon you're doing. So it's very crucial to educate people in silicon carbide and GaN technology, and of course gallium oxide, diamond, and whatever else is to follow. Okay, with respect of the cost, no surprise, silicon carbide device is about 3 times the cost of silicon, and the higher you get in current, you don't even have offerings, and the ones that you do are very, very expensive. Why? Because if you make a large area silicon carbide device to get a lot of current, there's a very high probability that you will incorporate a defect that will kill the device. Now, when I was at Northrop Grumman, I made devices that were very, very small for a power amplifier that goes into an aircraft that has a 350 mile, about 550 kilometers visibility. And that aircraft is in every US carrier, and it's silicon carbide that basically powers the radar. But that was a small device because it was more of an RF device. So then I said, okay, this looks great. I got 90% yield. Let me increase the size. And I did the odd, the bold step of increasing the size 100 times. And it pretty much dropped my yield 100 times. So, I wrote the paper. There was a massive amount of current. 2007 ice cream in Tokyo, the largest device, recognition. What I didn't put in the paper is that my yields were like 3 to 4%, okay? But you can work and make things better, right? It was just a demonstration at that point, and I was, very lucky at the time because I was in a company that had a fab that was, literally 15 meters from my office, and I would go and play and do process integration and come up with all the technology. It was a fun time. Okay, so if you look at this from Infineon, and this is a couple of years old, this is the system with silicon for the inverter for the PV, and this is the cost of the semiconductor. This is the system with silicon carbide. The semiconductor is 3 times more costly. So the question is, how can you pay 3 times more for the semiconductor and end up with a system that's cheaper, right? And here's the answer. Because with silicon carbide and GaN, you can go to higher frequencies, so you basically shrink the size of the passive components, you shrink the size of the heat sink because of the efficiency, and keep in mind, for mass commercialization, the cost savings at the system level must outweigh the higher cost of manufacturing silicon carbide devices. That's going to be your selling point, and that's where the education comes into play, okay? Because people that understand silicon carbide will tell you, yes, I'll pay more for the device at this point, but at the system level, advantages and lower cost. Okay, so some of the last remaining items, with respect to the material, minimize killer defects. BPDs are the big one. You have to improve the wafer planarity, eliminate defect generation during processing. When you process silicon carbide devices, you can generate defects, and I've seen that. It's at the implantation levels. Some people that I was funding at XFAB, no defects were generated. With other processes, defects were generated. So there are ways to do it to not generate defects. And of course, because of the gate oxide, the trapping, you have threshold voltage disability, and that's one reliability issue that needs to be resolved. And of course, you need to have a rugged device. Reliability and ruggedness, of course, are 2 separate things. Reliability is how well is the device going to work well during normal operation, right? Ruggedness is, oh my God, something really bad happened. How well does my device hold? That's the ruggedness. So you wanted devices that are as rugged as silicon. Otherwise, people will not make the switch. That's very, very important. So, the most important thing, of course, is short circuit performance. And we're very fortunate because we now have fast, intelligent gate drives that can basically shut down the circuit, detect a fault, and shut down the circuit in a very small amount of time. Just an example of what the BPDs, the bipolar defects, will do. This is a device. The minute I bias it, it drops here, okay? And it stabilizes here, and same thing right here. So that's undesirable. That's what you don't want. Interestingly enough, in those days when I was playing around in the lab, I took this device. It has BPDs. The BPDs led to degradation because the BPDs became stacking faults with energy. And then I went ahead and annealed the device for 96 hours at 350, and the device went back to the original state. So you have BPDs, you give them energy, they become stacking faults that compromise the performance of the device. You anneal the device, the stacking faults shrink back to the original state. Okay, of course, that's not a mode of operation. You don't want to be doing that. But BPDs are still there, and it's actually the last kind of big defect that we want to get rid of. So with that, at Power America, as I mentioned, we train 400 full-time students in projects, collaborations with industry, apprenticeships, and overall, we created educational events, webinars, tutorials, and so on and so forth. We engaged over 4,000 people. So that's a really good thing. And with that, I want to thank you for your attention and the opportunity to give this keynote. And I'll be here for the next 2 days. If there are any questions, please find me. I will not hide. Thank you so much.
I don't know, do we have any questions to Victor? Short one, because we need to go to next talk. Please, yes.
Simon?
One of the things you mentioned was about, sorry, this is Simon Price from Exawatt. You mentioned sort of figuring out the value of silicon carbide and wide bandgap power devices. And one of the issues that we identified a few years ago was that although the cost of silicon carbide devices is much higher than silicon, not only in PV, but especially in electric vehicles, it really doesn't matter that much because the impact on the system efficiency is so great that you can more than compensate for that increased cost with a decreased cost of the battery pack for a given range. And one thing I wanted to sort of point out to the audience, and possibly to you, is that this audience is in power electronics. We also cover lithium-ion batteries, and the cost of batteries for the first time in probably 10 years is about to go up. And so the value of silicon carbide to save battery costs and system cost is about to get markedly higher. So it's an amazing opportunity for the industry right now. Just wanted to make that point.
And that is exactly why we're silicon carbide and GaN have the growth that we see today, because we did find that one application where it makes a massive difference to insert silicon carbide and GaN. By increasing the efficiency, you reduce the size of the batteries, and that lowers the overall cost of the electric vehicle. Or for the same battery, you get the bigger range, and that's a key selling points for electric vehicles. So there's going to be a lot of growth, and I see, of course, people that are a lot younger than me, because I have been getting a lot older than I expected. So there's a bright future in silicon carbide and GaN. Pursue it. Thanks again.
Thank you, Victor. We need to go on. Now we will hear from Japan, from IST.
Hi, I'm Hiroshi Yamaguchi. Thank you so much for giving me an opportunity of presentation. Today, I'd like to talk about the recent progress in advanced SiC power device and modules. This figure shows the switching capability of the power devices. This area can be covered by the silicon power device technologies at present. However, silicon power device are facing the limits determined by the material property of silicon. Because of this, we have to recognize the fact that there are significant improvements of silicon cannot be expected. Thus, in order to overcome the silicon limit, our group is focusing on 3 wide-bandgap semiconductors: silicon carbide, gallium nitride, and diamonds. As shown here, the power electronics based on silicon carbide is a key technologies for realizing carbon neutrality, because there's superior switching characteristics here and here. The advantage of silicon carbide power devices are shown here. The first one is low on resistance. This means that the high efficiency and also reduction of cooling devices. The second one is high speed switching. This also means the high efficiency and reduction of cooling devices. And also high speed switching leads to the reduction of passive components such as filters. And third one is high voltage switching. In the case of the silicon carbide, over 10 kilovolt class power devices can be fabricated. And the last one is high junction temperature switching. This is also means a reduction of cooling devices by reducing the switching losses. And we can also expect the realization of the application for harsh environment and improvement of the transient performance, for example, called ride-through condition. Thus, we can expect that flexible power management realization by introducing the silicon carbide power converters. This table shows the present silicon carbide power devices. As shown here, 1 kilovolt class devices has already been commercialized. The most of R&D activity in this area are focusing on power module technologies and application-oriented systems. improvements. The high voltage devices, such as 3 kilovolt class, are developed based on the 1 kilovolt class device technology and are used for the electric railway system. The performance of trench type device is also improving. Maybe within a few years, trench type device will be widely used. And ultra high voltage devices are now under R&D. The expected applications are high voltage power supply for X-ray systems here and power system facilities here. In the next 2 slides, I will show the recent R&D result of lower voltage class power devices. From the viewpoint of application, the parasitic PN diode, body diode here, is a big issue because its characteristics is bad. In addition, it affects the reliability of MOSFETs. To overcome this problem, built-in Schottky barrier diode technology is introduced. The trench Schottky barrier diode is located here. The bad effect of the parasitic PN diode is eliminated by this Schottky barrier diode because the on voltage of built-in Schottky barrier diode is smaller than that of the parasitic PN diode. This is an example of superjunction MOSFET R&D results. Superjunction structure is very attractive for reducing the conduction loss of the device. However, as shown here, the device structure is complicated because we have to make superjunction column here. The fabrication process is therefore difficult. These devices are fabricated by introducing multi-epitaxial growth technology. By using this technology, the on resistance of superjunction MOSFET is greatly reduced compared to the conventional MOSFET here. The design, this table shows that present situation of silicon carbide power module or packages. The simple structure type module has been commercialized. In this area, the advantage of on voltage are mainly used at this moment. Of course, we'd like to use the distinctive characteristics of silicon carbide, such as high speed and high temperature operation, but there are some restrictions in the surrounding technologies. Although silicon carbide power devices show very high performance compared to silicon power devices, they required the improvement in the surrounding technology. For example, if we use high switching speed characteristics of silicon carbide, we have to improve the gate drive circuit and so forth. This is due to the significant difference of the switching speed here. The switching speed of SiC MOSFET is several hundred times higher compared to the silicon IGBT. So, for example, we have to improve the gate register and gate drivers as shown here, we have to use the high frequency characteristics registers and low output impedance and high speed drivers. And also, we have to make an improvement for signal insulation, power insulation, and logic circuit. And if we use some sort of sensors, we have to make an improvement. Many improvements have to be required, but if the design is appropriate, we can enjoy the extraordinary benefits such as very low switching loss. The design of the gate drive circuit is very difficult. Thus, the new approach is investigating. This photograph is a recently designed 1.2 kilovolt class SiC monolithic power IC. The SiC Cmos gate drive circuit are located just beside the power MOSFET. The design of Cmos gate driver circuit should be improved since the area of Cmos circuit is large. But the switching characteristics are excellent. The switching time is less than 10 nanoseconds in this case. By introducing this design, the difficulty in the drive circuit design is greatly reduced, and the advantage of silicon carbide, such as high switching speed, will be able to be utilized easier than before. Another effort for switching speed improvement in SiC power modules is shown here. The rating of these power modules is 1.2 kilovolt and 100 amps. In case of high switching speed operation, the switching surge caused by the wire inductance becomes a very big issue. To absorb the surge, a built-in RC snubber here, here, or here and here. The RC snubber is introduced. The minimization of the parasitic inductance of wire is also considered. In this case, the arrangement of the passives here are determined so as to minimize the wire inductances. For example, a dotted line shown here indicate that the path is located in the middle layer of the metallized substrate. As a result, the parasitic inductance between P and N terminals is about 4 nanohenry in this case. Another expectation of SiC power device is high temperature operation over 200 Celsius degree, which cannot be realized by silicon power device. The merit of the high temperature operation is a reduction of the cooling facilities. However, the reliability is the biggest issue for the realization. This problem should be considered from the viewpoint of chemistry and metallurgy aspect. In addition, the mechanical fatigue problem, which are caused by the difference of CTE, should be carefully considered. The fatigue failure problem are caused by the CTE difference and the fluctuation of the temperature. As shown here, the mechanical stress is applied to the contact interface when the temperature changes. The stress leads to the fatigue breakdown in the interface since the stress applied repeatedly here and here. Thus, the mechanical design has to be changed in order to improve the endurance for the stress. The wire material is changed to aluminum to copper because of the mechanical strength under the high temperature. In addition, a CT matching layer and top attach are changed in order to reduce the CT difference between copper and silicon carbide. Moreover, the bottom attach material is changed to sintered copper because the CT difference of SiC chip and the alloy solder is large. The design of the metallized ceramic substrate is also changed. The thickness of copper and silicon nitride are optimized in order to reduce the CT difference. As a result of the material choice is summarized in this table. As shown here, the CT difference is reduced in the case of the improved design. Therefore, the stress of the contact interface are reduced and the lifetime is greatly improved. The developed power module structure is shown here. By introducing the new design considering CT difference, the power cycle durability is greatly improved. In this case, the power cycle durability of the conventional structure is only about 3,000 cycles. However, the durability of the improved design exceeds 300,000 cycles. In conclusion, I'd like to point out the following. The commercialization of 1 kilovolt class simple design silicon carbide power devices have started, and the applications are expanding. The device using a built-in type silicon Schottky barrier diode technology are also at the commercialization stage. The present device R&Ds are mainly focusing on the superjunction type and high voltage type. The 1 kilovolt class simple design power modules have been commercialized already. The present power module R&Ds are mainly focusing on the surrounding technology, like the passive components. The requirements for high performance power modules whose voltage rating is 3 kilovolts or more are strongly expected for the purpose of the industrial applications. At this moment, we are expecting for realizing these 3 SiC technologies. The power IC and IPMs. These 2 technology realizes user friendliness and expand the applications. Also, high temperature tolerant power modules. This technology realizes the size and weight reduction of the power converters, which is very interested in the power converter users. Thank you for your attention.
So I don't think it's possible to ask questions to Japan now. So we have to keep it corresponds through emails. So now I will invite Herbert to present vertical GaN activities in Europe.
Good morning, everybody. Thank you, MITEC and team, for organizing this event and inviting me. I will tell you a little bit about Ultimate GaN. This is a project name of a EU-funded project as an enabler of green applications. And as we heard from Victor, it's necessary to have some assist and some help for these new topics, because the runway from research to application is partially done, but needs some way down. Yes, it's all about climate needs. Then I will give you a short overview on the Ultimate GaN project. And then the point of interest, gallium nitride and applications. But we will hear a lot of this in the next 2 days. Climate relevance, yes. Why is the public interested in our work in power electronics? And a summary. And I will give you also some gut feelings of Herbert, just as a seed layer of discussions, because we are discussing in the next 2 days gallium nitride and silicon carbide. And as we heard from Victor, sometimes it's a battlefield, what to use, and I will come to this. And the interest in our materials is simply gained by the need of electrification. Here you see on the slide the internet explosion, and you see 20 times the data within 10 years. And we are still growing exponentially in terms of data needed, data transferred, and data used in the Internet of Things and all the surrounded activities. And here you see, if you look at this graph, what is... Oh, I think this was the wrong button. Sorry for this. Oh, this is a pointer. Now I've got it. Sorry. One slide back. Yes, if you look at the power consumption, this ran totally flat, nearby flat in the last 10 years. And this was only because of all the research we have done as a power electronics community, but also the computing arena. It was simply flat. The data centers, when the data centers began, it was an old IKEA building. They put in a lot of servers, acclimatization, and that was a data center. And this was extremely energy demanding. And with all the work done, now data centers are streamlined. I think Gerald Debye could talk a lot about this, what we are doing in terms of efficiency in data centers. And, but this is not enough. All we have done, we will have a strong rise in the use of electric energy in all this stuff because of the still exponential growth of the data. And here our work is needed, is strongly needed to have a very efficient way of energy conversion. Because, to be honest, energy has to be converted because you need the different voltage levels. If you look at the transmission networks, you use the highest voltage for the most of the energy because otherwise you need a lot of copper. And so it's not only efficiency of electricity, but also of the materials. So we will have a lot of different voltage layers. So our business is coming in. It's energy conversion. And this is also the view of the International Energy Agency. And they are looking into efficiency. It's not our efficiency, but I take it as granted. Energy efficiency is a must. We have to use our energy very carefully. A lot of renewables and other topics not interested here. And this demanding curve here, this is a 1.5 degree scenario. So a lot to do to really stay at this level of climate warming. And this is why everybody's interested in our job. Power electronics was more or less hidden for many decades, but now people are interested and they are giving money. And here in this Ultimate GaN project, we are going towards the applications. So the title is Research for GaN Technologies, Devices and Applications to Address the Challenges of the Future GaN Roadmap. This we wrote 4 years before. And you see there are a lot of companies in, there are suppliers in, customers in terms, the entire value chain is in this project, and 50% is still research. So all your work of the research institute is still needed. And if I look for the next proposal, I see still a lot of research needed for gallium nitride. Even we have now products on the market and the market started. We will come to this. The structure of the project is very simple: technology, packaging, reliability, and application. And yeah, as you see, the research on the reliability is crossover all work packages. This is something, because the material is new, the application has to work with this. We have to learn a lot. We have still to learn a lot. And this is the reason why. This was a standard MOSFET at the beginning of the MOSFETs, yes. And this is the Gen 1 of the Cmos. Gerald, you will remember. And we are now at the Gen 7 of the Cmos. And you see, much smaller. And this is the first generation of gallium nitride devices. So it's all about shrink, making our technologies affordable. We heard a lot from Victor. What is the market? The market is when the price hits the demand. So the value for the customer has to be higher using the new materials than the old stuff. And here, Gen 2, this is where everybody is working on. You see, it's much smaller. And now it's getting difficult in terms of energy density. So you have to bring the current in, current out, and the temperature out. And with the surface is getting smaller and smaller, I think this one we can package effectively. This one, I have no idea for a discrete how to manage it in a device with the energy that has to be brought in, yes, and the temperature that has to be brought out. But ideal for integration ideas. So let's have a look in this. Yes, we met all the things in the very old project. We started in 2015 with PowerBase, making a device, having a pilot lie down, but the market, we were looking for the market where it is, where the market starts. And I will show you the whole figure afterwards. In the meantime, the market arrived. The challenges are still the same. So we started this project in 2019. We are going for higher power densities and all the new packages, dual-sided cooling. We have lifetime impact, better efficiencies needed. And I see we are still working on these topics. We are quite successful, but we are on the way. The learning curve for gallium nitride is still progressing. Higher current density, of course, migration issues and all this stuff, and the higher electric fields. Gallium nitride is a little bit more complicated than the silicon. Silicon, we are going for decades now, making the device smaller and smaller and smaller, and we are still on Moore's law in silicon. In gallium nitride, it's much more complicated because we managed the first generation, but all with the reliability issues we had, we managed it to qualify it, but shrink as we do it in silicon, you can forget it. You need additional ideas here. And now looking to the applications, yes, the market started. 2014, I showed a similar figure, and we had to wait 6 years, but now it's here. And this is why it was much more difficult than everybody expected. And now we see already in the first generation a kind of economy of scale. We hadn't economy of scale, and this is, I had a lot of partners doing applications in gallium nitride. The technicians were delighted by the properties of GaN, but when they went from pre-development to development and decision what product to build, gallium nitride was out. The chief buyer was sitting at the table, said, this stuff is much too expensive. We expected the price for gallium nitride to be half of that at that time, and GaN was out. And now we can manage this. And this is why I believe that the strong growth we see already will be ongoing for the next years. Even we have to manage a lot of questions to answer this. And what you see here, it's power supply. The market, the Kickstarter for the market is our mobiles and the tablets having a lot of lithium ion in, and everybody wants to charge quick, and you want to charge from your wall box. So not a special wall box, but with a normal plug having a small DC cable. No one likes the AC cables at your adapter for the laptop. And it's doable. What I see in the next years, we will get rid of all these adapters, having a plug in the wall, having a small DC cabling, and this is much better for traveling, and this can be done with gallium nitride. So here a strong future, and a lot of other applications, and I will show a little bit of this, will follow. So this we heard already. What we have silicon carbide, and gallium nitride. Gallium nitride, the only one what is lateral. So yes, the physical properties we have heard already by Victor. But it's, if you look at the electromobility, this is a little bit misleading. Because in silicon carbide, it's not the mobility in the volume, it's the mobility at the channel. And this is still very poor. And it's gallium nitride with a two-dimensional electron glass. This is about 20 times higher. So Herbert's gut feeling, you cannot betray physics. So for the lower voltages, I see GaN in a very favorable position. And for the higher voltages, as everybody said, yes, it's hard to compete with silicon carbide. And here I will show a little bit of vertical gallium nitride. And this is will be a hard match and a long way to go for the vertical. And here I will skip this. Yes, we have made several use cases with customers. So bringing pre-developments into these projects. So we have research and pre-developments with products that should be sold on the market afterwards. How much time I still have, Mitek?
Yes, you are fine. 5 minutes.
Oh, okay. But I'm always take more time, therefore I prefer to ask. Yes, the benefits of gallium nitride in telecom applications. LTEC is being the second time a partner with us in these projects, and they are making really good stuff of using gallium nitride in a proper way. And this is what they did this time. And if you look, yes, efficiency target, 98%. Maybe not perfect for a paper, but excellent for a product. They had even more. So they were over 98, but they decided out of economical reasons to stay with the 97.9. But this is what we have to do in reality, to find the point where it matches the market with the efficiency. And somebody has to pay for gallium nitride. And here, this is also, for me, a very good signal. In the last project, they did a server power supply with 97%, which was 2% over the market. So really, 4 years ago, it was the most efficient server power supply. And they used it in the field. So you have it in the field with a 150,000 parts per supplies they used, with even more gallium nitride switches. And we had 3 returns, but these returns were not caused by the technology. This was topside cooling, and the joint of the device to the cooler was bad. It was overheating, but 150,000 and no technology related field return in an IP65 applications. And this is a signal, yes, gallium nitride, if you look at the yields and all the intrinsic reliability of gallium nitride is still on the learning curve, absolutely. But we managed it with really good stress testing, understanding the mechanisms to sort out the devices which could fail in the field. So there's a lot of know-how in how to test it, how to stress it, that you can manage it to have very good. And so I see a bright future for gallium nitride. Even we have still to learn a lot on the terms of defects, on reliability. But as a message into the audience, I believe we will manage this. And we did it also for silicon carbide. Also silicon carbide has a higher defect level than silicon, and we manage it to have good quality in the field. So one thing we also did in this project is radio frequency gallium nitride power switches on silicon. Because a radio frequency is very clear, it's GaN on SiC. It works, it's fine, and if you look into space or something like this, everybody will pay, nobody cares. If you look into 5G and the rollout of 5G, price matters. And GaN on silicon, radio frequency GaN on silicon, can be much cheaper than GaN on silicon carbide. And in this project, we demonstrated that we come close to the same properties of GaN on silicon carbide. And here it was not to be better than GaN on silicon carbide, but we are very, very close and ready for 5G, and I see a rollout. But also a competitor of us had a mailing this week, or last week, that they will bring RF GaN on silicon. So here, yes, the rollout, radio frequency on GaN on silicon, it works, and it will work and has good properties. And the second thing you see here, it's all about miniaturization and integration. What we have seen and discussed already today, the vulnerabilities of GaN. In the first project, all partners had problems. 4 years later, everybody can work with GaN. So Victor, thanks to you and all the others that made good education, because our customers, our research partners, can work with GaN. I don't get so many questions and returns because the vulnerabilities of GaN, the 2-deck is really great, but it's saturating at a point where everything else is destroyed. We are used to silicon with having under short circuit conditions a saturation of the channel. You can wait very long until the 2-deck saturates. So we have to be very quick. And all partners telling me, Herbert, we like the GaN, we like the properties, but we don't like to handle all this stuff. We want to make it have it easier. We want to have the security, so the ease of integration integrated. And then the high frequencies. The train is going towards integration, and GaN is ideal made for this. So yes, here another very interesting application for LiDAR. For example, if you use LiDAR in the mid-range, you need a very strong laser pulse. But because of safety reasons that your eye is not affected, you have to limit the energy of the pulse, of the laser pulse, and therefore it has to be a pulse within 5 nanoseconds. And to make this happen, gallium nitride is ideal, and then you need low parasitic inductances. You need an integrated version to make this happen, but it will work. And last but not least, yes, microgrid applications. This is very interesting, and this is what we also see in the car. The first where gallium nitride is really going to happen is in all DC-DC conversions, because then you are free choosing your frequency, and here gallium nitride really pays off, but only if energy density is a value for the customer. So the difference between research and the market is it has to pay off. And in 5 years, no one will discuss silicon carbide or silicon anymore. It's only a question of price performance. What's the value for the customer? As Victor explained, what is the system benefit using this stuff towards the price? Nobody is interested in silicon carbide and silicon anymore in the physics of it. This is our job. Nobody is interested in it, really. It's just a switch. And the same will happen with gallium nitride a few years later. Now we are discussing gallium nitride. Is it feasible for this application? It is long-lasting. What's it with reliability, long-term reliability? In 5 years onwards, this will get less, and in 7, 8 years, no one will discuss if we are using this or that. So, vertical, yes. Vertical, we are doing semi-vertical in this project, just to get a feeling how GaN is reacting. And here you see we are not at the benchmark, but we are doing this job in the semi-vertical just for the validation, to get good models that we can say. For me, it's undecided if vertical GaN really can compete with the silicon carbide, not using the 2-deck. So, because my time is running out, Herbert's vision of the future gallium nitride device, it's really a vertical 2-deck. And here we have Swedish partners like Hexagem, Swigan, and Rice in our project. And Hexagem is doing technology is very simple. They have a wafer with a mask with holes, and then they are building nanowires on it. And the nanowires, after a certain height, are defect-free. If you overgrow it with a P-GaN, having a vertical 2-deck all around these nanowires, and then having them in parallel as a field. This is Herbert's dream, a fully vertical 2-deck as an ultimate device. This is then really ultimate GaN, but here I would say it will take us 10 years to get there. But then, yes, for me, this will be the top. I'm waiting for this. And I'm waiting for all researchers helping me to realize my dream. Climate relevance, yes. Why we are doing this, why the public is interested in our work and is funding this work, is very easy. If we increase for all the data stuff and the PV sector, the efficiency by 1%, it's 20 of these power plants. This is at the Danube in Vienna, and it's 1 terawatt hour per year. So you need 60 of this to power Austria electrically. And now with getting out of the gas, it's even more. And you see 1 percentage point will make 20 of these power stations. And this is the relation of our work. So let's finalize. To be very quick, yes, we will see a lot of interesting applications in the next 2 days. Downscaling of power of GaN is still a job accompanied by a lot of research. We need materials, know-how. Still, it's not done. Gallium nitride is working now in the field, but it's not done. We are on the learning curve, in the mid of the learning curve, and all together, yes, it's worth fighting for every percentage point of efficiency. Thank you.
Thank you very much, Herbert, for this inspiring talk. And we have, yeah, I don't know if there are any questions.
Thank you very much for an excellent presentation. I have one question. As you pointed out, the lateral GaN has this advantage of the very high mobility in the 2D electron gas. When you made your vertical devices, what type of mobility did you see Is it comparable to this lateral, or where does the mobility stand?
By far not. So having gallium nitride with an oxide as a MOSFET, we have to do a lot of research. IMEC is doing the research work. I can send you the material, which is free. And yes, it's still deep in research. And finally, I decided if there are applications using the advantage of a gallium nitride device compared to a SiC device if you're not using the 2-deck. From Herbert's gut feeling is, if you're going for gallium nitride, please use the 2-deck, because this makes all the difference.
Okay, and then a second part to this question. With a lateral device, of course, as you go higher in voltage, there's a higher separation of gate to drain, so that the device becomes larger, which can be prohibitive because you're taking more lateral space on the wafer. The second thing is the buffer layers to withhold, high voltages. It's special technology.
We are working for this, and this is also done by IMEC. They demonstrated a 1200 volt lateral, but with a GaN on QST. This is a polyon aluminum nitride substrate, so it's CTE matched. So what you said and what Hiroshi said, you have to go for the CTE match in the epi, and then you can grow much thicker epis. They achieved epi stack of 15 microns plus, I think, up to 18 micron, crack-free on 6-inch, and with a diameter 8 micron thick buffer stack on 8-inch. So on 6-inch, they produced 1200 volt devices. And now I'm looking for the community. Please ask them. You can ask Benoit Baccarat from IMEC. Where's the application really making the difference? Because what we learned with the Cmos, when we came with the Cmos, Gerald will remember, there was no business. It was a totally new one. People had to learn how to use these devices. So I cannot say there is no market for 1200 volt lateral GaN, but we need your help to see where are really the differentiators to use it. But 1200 volt is doable, but from my point of view, only with a different substrate on 6-inch in the moment.
Thank you. Thank you so much.
So if there are any more questions.
First, thank you for your presentation. I have a question regarding the automotive applications. Right now, you can see that the automotive applications switch to the higher voltage due to the benefits that they can get from efficiency. Now we have a system in the 800 volt that the voltage can reach around 950 volt. And we can see, for example, the latest product of the Mercedes, that they have a 920 volt system that the voltage can reach around 1.4 volt. What do you think about the GaN application in those?
My view with what I see in automotive is they want to keep it simple. I see them more in the next years sticking with the higher voltages with the silicon carbide, because the silicon carbide in automotive now is a tick mark. But this is not for all the time, but this is what Herbert's gut feeling is in the moment. They're acting rather conservative. If you have a more complicated scheme on a multi-level regime, I think they will not take it they will do it in research, but it will take some years. What I see is OBC and DC-DC. That's what you all is saying. They are asking us, they are asking you, and then they are making this crystal ball. But this crystal ball is, I think, very clear now. It was more diffuse 6 years ago, but now I'm their opinion and see. But let's hear Gerald de Boy afterwards on that, because he will more go in detail.
Let's take it as the last question, because we are consuming all time for your coffee break.
Thank you very much for the presentation. What about the short circuit capability of GaN? So this is something what I see in application that's much less than the silicon carbide?
Very
or-
simple. You cannot betray physics. You have to do, as we have seen it with Victor's slides already, you have to do it in the system, and you have to go for an integrated approach. People don't want, they can do it. The most, many customers can do it, but they said, I don't want to do it. Yes, you have to integrate it. You have to need a sensor on the chip, and then if it's a system in package or a system on chip approach, I don't care. Customer don't care. It's all the ease of use, and then you have the protection inside, and you can use it easily. So this is my opinion. Very clear, it has to be integrated.
Okay, thank you, Herbert. And now we have a coffee break. Hallo? Hallo?